projects. In this video, we are going to explain about the project titled Knee Osteoarthritis Detection using an improved CenterNet with pixel-wise voting scheme. Introduction. Knee osteoarthritis is a chronic degenerative joint disease affecting the knee, often characterized by progressive cartilage loss, inflammation, and changes in the joint structure. It leads to symptoms like joint pain, stiffness, swelling, and reduced mobility. As a chronic condition, it can significantly impact a person's quality of life. MRI, magnetic resonance imaging, X-ray, and CT scans are common imaging modalities used to analyze KOA, knee osteoarthritis. MRI provides detailed images of soft tissues, while X-ray, being more cost-effective and widely accessible, is commonly used for initial assessment due to its ability to visualize bone structures. CT scans offer detailed cross-sectional images but are less commonly used for routine KOA assessment due to higher cost and radiation exposure. The Kellgren-Lawrence grading system is a radiological classification used to assess the severity of KOA, knee osteoarthritis, based on X-ray findings. It categorizes the disease into 4 grades: grade 1, grade 2, grade 3, and grade 4. Early detection of KOA, knee osteoarthritis, is critical for initiating timely interventions and treatments. Early stage management strategies such as lifestyle modifications, physical therapy, and medication can potentially slow down disease progression, elevate symptoms, and improve overall joint health. Additionally, it allows healthcare providers to plan appropriate care and prevent potential complications associated with advanced stages of KOA. Existing methods, including machine learning based algorithms for KOA, knee osteoarthritis detection, and grading, face challenges related to accuracy and precision. These methods struggle with accurately identifying subtle changes in joint structures or differentiating between varying degrees of disease severity. The proposed project aims to address these challenges by leveraging advanced deep learning techniques. It specifically plans to customize a CenterNet architecture utilizing DenseNet 201 as a foundational technique. This customization aims to enhance the accuracy and reliability of KOA detection and grading across all disease stages, potentially improving diagnostic capabilities and treatment planning in clinical settings. Objective. The primary goal is to create an advanced deep learning model tailored for detecting and classifying knee osteoarthritis KOA using knee images derived from X-ray scans. The aim is to improve upon existing methods by leveraging deep learning techniques for more accurate and efficient detection and classification of KOA. The proposed model is built upon a customized CenterNet architecture incorporating a pixel-wise voting scheme. It relies on DenseNet 201, a convolutional neural network known for its efficacy in feature extraction, as the base network. This combination aims to optimize feature representation and localization for accurate KOA detection within knee images. The model's core objective is to autonomously extract highly representative features from knee samples. Furthermore, it aims to provide precise bounding box predictions through a weighted pixel-wise voting scheme. This method enhances the model's ability to precisely delineate and identify areas indicating signs of KOA within X-ray images. The project includes a technique called knowledge distillation. This approach simplifies the model complexity without increasing computational requirements. It transfers knowledge from a more complex network to a simpler network, ensuring efficient utilization of computational resources without compromising performance. The proposed model's performance is thoroughly assessed and validated through various experiments. It is anticipated that the model will exhibit superior performance, showcasing high accuracy over both testing and cross-validation datasets compared to existing techniques. This estimation is based on the model's ability to accurately detect and classify KOA in knee X-ray images. Software and hardware requirements. Software requirements of the project are: software is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing necessary libraries and packages in the chosen programming environment. These include libraries such as NumPy for numerical operations, Pandas for data manipulation, Matplotlib or Seaborn for visualization, and frameworks like TensorFlow or PyTorch for deep learning implementation. Importing packages set up the groundwork for subsequent data handling and model development. Exploring the dataset. This section involves acquiring and understanding the dataset related to knee osteoarthritis KOA. It involves obtaining knee X-ray images from a specific dataset dedicated to KOA or utilizing data obtained and pre-processed from RoboFlow, a platform that facilitates data preparation for machine learning tasks. Exploratory data analysis EDA includes assessing data quality, understanding label distributions, and visualizing sample images to gain insights into the dataset's characteristics. Image processing. This stage involves pre-processing and augmentation techniques applied to the knee X-ray images before model training. Using image data generator, a utility in libraries like TensorFlow or Keras for data augmentation, including operations like rescaling the image for normalization, applying shear transformation to simulate angular distortions, zooming to focus on specific areas, horizontal flipping for mirroring, and reshaping for standardizing image dimensions. Torch vision based processing for detection. Utilizing PyTorch's Torch Vision library specifically for processing and preparing images to train the detection model. This step involves additional transformations or pre-processing specific to CenterNet model architecture or PyTorch requirements. Building the model. This phase involves constructing the improved CenterNet model architecture enhanced with a pixel-wise voting scheme for knee osteoarthritis detection. Customized CenterNet architecture, utilizing a modified or enhanced version of the CenterNet architecture tailored for precise detection of KOA within knee X-ray images. Pixel-wise voting scheme, integrating a voting mechanism at the pixel level, which involves aggregating predictions across neighboring pixels or regions to enhance accuracy in identifying areas indicating of knee osteoarthritis. Training the model. This stage involves feeding the pre-processed knee X-ray images into the customized CenterNet model, fine-tuning its parameters, and optimizing its architecture using a training dataset. The model learns to identify patterns and features associated with knee osteoarthritis through an iterative process, adjusting its internal weights based on observed errors to minimize prediction inaccuracies. Flask framework with SQLite for sign up and sign in. This module utilizes the Flask web framework, a Python-based framework, along with SQLite, a lightweight relational database management system, to create a user authentication system. It enables users to register, sign up, and authenticate sign in before accessing the application. This feature ensures data security and access control within the application. User upload an image for analysis. In this stage, users interact with the application's front end to upload knee X-ray images they want to analyze for knee osteoarthritis. This functionality allows users to input their own data or images into the system for analysis. The given input is pre-processed. Upon uploading the image, the system pre-processes the user-provided knee X-ray image before feeding it into the trained model. Pre-processing involves applying the same transformations and normalization techniques used during training, ensuring the input aligns with the model's expectations. The trained model is used for predicting the result. The pre-processed input image is passed through the trained CenterNet model, which applies its learned knowledge to predict regions or areas within the image that indicate the presence or likelihood of knee osteoarthritis. The model utilizes the pixel wise voting scheme incorporated during training to provide predictions. Final outcome is displayed through front end. The results of predictions generated by the model are presented to the user through the application's front end. This display includes visual overlays on the input image, highlighting regions identified as indicative of knee osteoarthritis. Users can view the outcome, enhancing their understanding of the model's prediction and aiding in decision making regarding further medical examinations or interventions. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is CNN, Convolutional Neural Network. CNN is a class of neural networks primarily used for image related tasks due to its ability to effectively learn hierarchical representations of features. It comprises layers like convolutional, pooling, and fully connected layers. Convolutional layers extract features by convolving learned filters across input images to capture spatial patterns. Pooling layers reduce spatial dimensions, and fully connected layers perform classification based on extracted features. In the context of the project, CNN forms the basis or a component of the model architecture. It aids in feature extraction from the knee X ray images, enabling the model to identify intricate patterns associated with knee osteoarthritis. Deep CNN, Deep Convolutional Neural Network. Deep CNN refers to CNN architectures with increased depth, comprising numerous convolutional layers stacked sequentially. Deeper architectures enable the network to learn more abstract and complex features from input data. Deep CNN indicate a variant or an extension of the conventional CNN architecture used in the project. This deeper architecture enhanced the model's ability to extract nuanced and intricate features from knee X-ray images, potentially improving the accuracy of knee osteoarthritis detection. DenseNet 201 backbone for CenterNet voting. DenseNet 201 serves as the foundational architecture within CenterNet, offering robust feature extraction capabilities for intricate pattern recognition in knee joint images. CenterNet is an object detection framework adapted here to identify and localize key points linked to knee abnormalities related to osteoarthritis. The pixel-wise voting scheme enhances accuracy by aggregating multiple predictions at the pixel level, refining the localization of osteoarthritis indicators and reducing false positives. Combining DenseNet 201 with CenterNet and applying pixel-wise voting aims to improve the precision and reliability of knee osteoarthritis detection from medical images. DenseNet 201 is a convolutional neural network architecture known for its dense connectivity pattern, where each layer receives direct inputs from all preceding layers. This design promotes feature reuse and facilitates gradient flow throughout the network, leading to better feature propagation and elevating the vanishing gradient problem. In the context of CenterNet, which is a key point based object detection framework, DenseNet 201 serves as the backbone of feature extractor. Its robust feature extraction capabilities enable CenterNet to efficiently extract informative features from knee X-ray images. The network learns from the dense connectivity patterns of DenseNet 201 to identify key points or regions associated with knee osteoarthritis in the image. As an extension, we used other deep learning models to produce a more robust and accurate final prediction, and we also utilized YOLO family for detection. Comparison graph. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute the project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on sign in. So here we need to enter the username and the password which we have registered, and then click on sign in. We have logged in successfully. So here we can see a prediction link. So we can execute the project using both classification and detection. First, we will do the classification. So click on classification here. So here we need to upload the image. After uploading the image, we will predict the stage of the knee osteoarthritis. So click on choose file to select the image. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as the patient is diagnosed with stage 0 knee osteoarthritis. Let us upload some more images and check the stage. Click on choose file. Select the image. This is the uploaded image and it is predicted as the patient is diagnosed with stage 1 knee osteoarthritis. Click on try again, choose file, select the image, click on open. This is the uploaded image and it is predicted as the patient is diagnosed with stage 2 knee osteoarthritis. Let us upload some more images. Click on upload. This is the uploaded image and it is predicted as the patient is diagnosed with stage 3 knee osteoarthritis. In this way, by uploading the image, we can predict the stage of the knee osteoarthritis. Now click on prediction link. Now we will do the detection. So click on detection. So here we need to upload the image. Click on choose file, select the image, click on open, click on upload button. So here we can see it is detected as stage 0 and it is represented by a red color bounding box. Now let us upload some more images. Click on choose file, select the image, click on open. This is the uploaded image and here we can see that knee osteoarthritis is detected by a red color bounding box and on top of the bounding box we can see the stage which is stage 1 and here we can see the probability score which is 0.51. Let us upload some more images. Click on choose file, select the image. This is the uploaded image and here we can see the detection with the orange color bounding box and on top of the bounding box we can see the stage which is stage 2. In this way, by uploading the image, we can detect which stage the patient is suffering with. Now click on sign out button here. The conclusion of the project is the model designed for knee osteoarthritis KOA detection and classification based on an improved CenterNet architecture with a pixel-wise voting scheme and DenseNet 201 has the backbone, has showcased encouraging performance metrics. This includes high accuracy, precision, recall rates, indicating its effectiveness in accurately identifying and classifying KOA in knee X-ray images. The utilization of pixel-wise voting scheme coupled with DenseNet 201's dense connections in the feature extraction process significantly contributes to the model's improved performance. The pixel-wise voting enhances the accuracy of identifying KOA-related regions, while DenseNet's dense connectivity patterns enable effective extraction of highly informative features from these regions, improving the model's ability to discern subtle patterns indicative of KOA. The model demonstrates a remarkable capability to precisely identify the region of interest ROI within knee X-ray images, specific areas or regions indicative of KOA. Additionally, it effectively extracts and represents essential and distinguishing features from these regions. This precise feature extraction is pivotal for enhancing the model's predictive abilities, enabling accurate classification of KOA severity. The proposed system's proficiency in early detection of KOA and its ability to assess the severity using X-ray images holds significant promise for orthopedic surgeons and radiologists. It empowers these healthcare professionals with a reliable tool for early diagnosis, aiding in prompt intervention and treatment planning for patients suffering from KOA. The robust nature of the model allows it to generalize well to unseen or new knee X-ray images. Its ability to accurately identify KOA-related features as previously unseen data indicates its potential for practical deployment in real-world scenarios. By providing accurate and efficient KOA detection using X-ray images, The proposed system has the potential to streamline the diagnostic process. This efficiency can lead to time saving benefits for both patients and healthcare professionals, allowing for quicker assessment and appropriate interventions, ultimately improving patient care and management.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.